Hello, everyone. Welcome back to our HPL seminar. I hope you all had a wonderful summer and are ready for the new school years. First of all, I'm your new Ian, and my name is Enkwan Mu. I will be the seminar facilitator for this school year. Before we start our seminar, Walter has a quick announcement to make.
Very nice to have a big microphone here. So my name is Walter Herzog. Some of you that I don't know yet are probably 393, 395 students. And if you are, yes, you're at the right place. And so what you do is listen to the seminar very carefully. And then after the seminar is done, we'll have a 5-minute break that everybody will leave the room and so on. You can grab a coffee or whatever. And then 5 minutes after the seminar, we meet back here in this room again, and then you'll see what we do with the class. So if you are in 393, 395, watch, observe, think, and come back after the seminar.
Thanks, Walter. So it's my pleasure to introduce our speaker of today, Dr. Saied Jalal Aboodarda. Jalal is a postdoc fellow with Dr. Guillaume Millet. He obtained his master's degree from Isfahan University, Iran. In 2012, Jalal received his PhD degree in exercise physiology and exercise science from the University of Malaysia, a beautiful country. In his PhD thesis, Jalal studied acute neuromuscular, hormonal, and morphological responses following variable external resistance exercises. Before joining HPL, Jalal worked as a research associate with Professor David Ben at Memorial University for 3 years. So at the University of Calgary, Jalal is interested in understanding the central and peripheral fatigue in healthy individuals and patients with multiple sclerosis. Jalal has published 34 articles and presented his work in 25 international conferences. So one of his proudest achievements in academia so far is being able to conduct his research in HPL. Now, outside of work, Jalal loves spending time with his family and reading neuroscience blog. And believe it or not, before becoming a dedicated and passionate scientist like Jalal, he was actually hoping to work in a bakery shop. But he will not share his recipe with us today. Instead, he will tell us more about the effect of fatiguing exercise in one limb on the neuromuscular functions of the contralateral limb. Please, Jalal.
Along here today. I know probably today is the first day that biomechanics, exercise physiology, all the fields came together. If I'm not mistaken, it was biomechanics specifically for HPL. No, yeah. So thank you very much because I know many of you guys are from you have biomechanics background, but you came to this session, and I hope you find it interesting. So, question is very simple. If you fatigue one limb, is it the effect of fatigue is going to be a local effect, or it's going to be a general effect? If you fatigue one limb, you're going to see the effect only in that limb, or no, it has a global effect. It may affect other parts of your body as well. So very brief background, fatigue is defined as any reduction in power output or force. And conventionally, it's divided into central and peripheral mechanism. Central means brain and spinal cord, and peripheral means local muscles. I would like to see how I can open my discussion that it doesn't become too much confusing for you guys. I said the simple question, is fatigue a general phenomenon or it is a local phenomenon? Why it is important, basically. Someone might say, why you are interested to see if fatigue is local or general? Because we do single movement tasks every day, from rehabilitation, therapeutic, recreation, athletic setting. You will see that we do simple movement tasks every day. I'm pretty sure you have seen people that they had leg injury or surgery, and after they opened the cast, they had a huge atrophy in their leg. Now they have to do single movement exercise to get the leg back. Or if they exercise bilaterally, or if they exercise the strong leg, what's the effect on the weak leg? And I said in rehabilitation, we have many examples that people do single leg or single limb movements. What's the effect in the contralateral side? Before I start, I would like to give a very brief tour about our corticospinal system. Very simple. Brain, spinal cord, muscle. Brain sends signals to spinal cord conveys the signal to our muscle. If we go slightly deeper, we will see that the primary motor cortex in our brain, which in an area around here, relays signal to the spinal cord. So these signals are going to go to the contralateral side. You know that our left hemisphere controls our right-hand side of our body, and right hemisphere controls left-hand side. So at the level of medulla, which is somewhere around here, these nerve bundle, which if you would like to know, it's around 100,000 nerve cells, axon of 100,000 nerve cells, are going to decussate to the contralateral side. So these nerve cells are going to go from this side, decussate to the contralateral side, and go to from right hemisphere, go to the left side of our body. It generates a synapse at the level of spinal cord, and these synapses are going to bring, this is alpha motor neuron, brings the signal to the muscle. So brain, spinal cord to the muscle. This is a very isolated kind of system. How it is possible that you are exercising one arm, signals go down, but the other arm could be affected? So the first question is how contralateral signaling pathway could be facilitated. Yes, it can happen. Where? Several layers or several locations. The first location is at the level of corpus callosum in our brain. Corpus callosum is a very thick nerve bundle which get the signal from one hemisphere and move it to the other hemisphere. That's why we can walk. When we walk, the coordination of our legs is because of corpus callosum. Or we can do things with our hand rhythmically. So corpus callosum is a kind of mediator which connects two sides of our brain. The other thing that happens in our brain is if I just explained about corticospinal tract, signals go down at the level of caudate medulla, decussate to the contralateral side. I just told you, right? However, 90% of these nerve bundles go to the other side. 10% go directly down. So these hemisphere send signal to the other side, but 10% of it go to the ipsilateral side. Forget about this slide because it's our somatosensory system. It's a bit complex. It's not really necessary. I wanted to remove it. I forgot. Forget about it. So the other pathway that may change our contralateral side motor programming is that, yeah, signals go to the other side. However, at the level of brainstem, signals have bilateral motor programming. This slide could be a bit confusing, but I'm going to ask you a question. If you want to do squat, single leg squat, can you say one of your glute muscle, you relax, I just want left glute to be activated? No, you can't. Can you say your abdominal muscle, okay, rectus abdominis or external oblique right, please go to silent, I just want to activate? No. So all of our muscles in the core area, which are contributing significantly on single movement task, have bilateral motor programming. And finally, at different areas of our brain, at different areas of our spinal cord, as you can see, there are collaterals, which signals go down, however, jumps to each side. You can see that signal jump to both sides and distribute signal to both left and right-hand side of our body. So it is possible to have a kind of leaking from one, I don't know if leaking is a good word or not, but yes, signals are going to be distributed in both sides of our body. The major question, does this system facilitates fatigue go from one limb to the other limb? This is the thing that we are going to discuss about it today. In 2015, my student Israel Halperin, he's a PhD student in Cowan University now, and my supervisor David Bain wrote a review article about non-local fatigue, and they brought this term, non-local fatigue, and they defined it as any indication of temporary deficit in performance in non-exercise muscle groups. I was supposed to be a part of this paper, but then I was like, this is too general term. This is too early to call this non-local muscle fatigue because we really do not know if it happens or not. Anyway, so they brought a very comprehensive review of the literature, and they figured out that, so let's concentrate. We fatigue one limb and we test the other limb, all right? In this study, they found that when they fatigued, in this review, they found that when studies fatigued one limb and tested the other limb, this is an important fact, when they tested the other limb only with one contraction, in many cases, they didn't find any drop in force. So they fatigued this leg, but in the post-test, they only did one MVC in the non-fatigue leg. MVC didn't change. Or some had good rest. This is my paper. We had good rest, like 30 to like 2 minutes rest. In this case, the level of, this is not significant. This is just the effect size. It was non-significant, but with a large effect size. Or, for example, here, single leg movement, again, no significant difference. And here, there is 30-second rest. What I want to say is that it seems when you are doing a task, a fatiguing task in one limb, and you test the other leg, if this test is very brief, you're not going to find any difference. And we did this study again in 2014. The test was 5 sets of knee extensions, fatiguing, like devastating. It was really, really fatiguing. 5 sets of knee extensions to maximal force output. The level of lactate reached 12. Like very high. But we wanted to know after these really demanding tasks, fatigue is going to change biceps muscles. So what we did one MVC at post-test, and then we did 12 MVC consecutively. At one MVC post-test, when they only did 5-second contraction, there is no difference between control and fatigue session. So fatigue didn't show up in arm muscles after a very, very demanding task in our legs. However, when we did 12 contractions back to back, I think every 10 seconds, from contraction number 8 to 12, as you can see, the path is going to be different between fatigue day and non-fatigue day. It means what? It means when it is only 5-second contraction, I say, okay, that's fine. It is just 5. I'm tired, but I can do it. It's just 5 seconds. There is no difference. However, as you can progress through the number of contractions, then your brain starts to think, hey, you are already tired. You have a very tiring, you did a very tiring task in your legs right now. So try to be careful of yourself. Homeostasis. Safety becomes a factor. So now from this level, from contraction number 8, force is going to drop more in the fatigue and stays high in the... Is this clear? I just want to make sure that you get this idea that if the contraction is brief, brain doesn't care. But if the contraction is pretty long, the brain is going to hold back. Hey, wait, you are tired. Homeostasis. Safety is important for you. This study, we did another study in 2016, 6 contractions, 6 MVCs after fatiguing one arm, testing the other arm. As you can see here, there is no difference when there is enough rest between contractions. Like here was 45 seconds rest between each contraction. There is no difference between 2 conditions. Another study, I fatigued one leg and tested the other arm, like contralateral upper lower. The same thing. There is no difference between 2 conditions. This is time effect. These 2 symbols are time effect. Please do not be confused. This is time effect. This is not condition effect. So we got back to these two major studies, which NIBO 2004, if I'm not mistaken, I removed one of the studies. NIBO 2004, he says, when the task is very brief, you are going to mobilize all of your willing or all of your mental capacity to do that task to avoid reduction in force. And another evidence said, when the task is very brief, other area of your brain is going to come to help. Primary motor cortex, like ipsilateral sensory motor cortex, prefrontal cortex, orbitofrontal cortex, and anterior cingulate cortex, all of them, they're going to come in to help to do that brief task. But doesn't necessarily mean that it's going to happen during long-term task, right? So my question in this study that we did, we did this summer was, does your brain pace during contraction like 30 seconds or 60 seconds MVCs, maximum voluntary contraction, or not? So we did this study this summer with two of our brilliant undergrad students, Cindy and Maddie, that you're going to see their pictures soon. So 6 sessions, 12 participants came down to the lab for 6 sessions. In each session, we did 1 pre-test, 1 post-test. This was consistent between sessions. In the first 3 sessions, actually when I say first 3 means it was randomized, but let's concentrate here. We did pre-test, everything measured in right leg. So pre-test, post-test. In another session, we did pre-test, but before they go for post-test, they did 30-second contraction, fatiguing contraction, maximum voluntary. So you have to go as hard as you can for 30 seconds. In another session, they did the same, but they did the contraction for 60 seconds. They repeated identically, they repeated exactly the same thing in another 30 seconds, in another 3 sessions, but instead of rest, here was rest. This leg didn't do anything. Here, this leg did 60 seconds fatiguing contraction. I do not know, have you ever done 60 seconds MVC or not? It is not fun. 60 seconds MVC hurts. We had a couple of participants, they were very nauseous. They really wanted to throw up. So it's a very demanding task. It's not just sitting here and say, it's 60 seconds, I can do it. No, it's not the case. So we wanted to know if we have a very, very demanding task, which is 60 seconds fatigue in one leg, is it going to affect the pattern of motor programming and force output and everything in the other leg or not? So remember, this is identical. These 2 sessions are identical. We just want to know what's the effect of these 60 seconds fatigue in this leg on the parameters in the other leg. And similarly here, these 2 sessions are identical. The only difference is here. So we want to know how much is the force, initiation of the force at the beginning of contraction, as well as here at the post-test. So here, again, these 2 sessions are identical. The only difference is 60 seconds contraction here. And we want to know what happens at different stages of force output, at the beginning of here, at the end. And the slope. So we wanted to know if 60 seconds is going to change the slope of force. Probably at the end, because they have already 60 seconds contraction, probably they are going to end up at the less force production. We wanted to know that. So Maddie and Cindy, they came down to the lab, they volunteered to do this study, and Dr. Mie and I, together, we determined the setup protocol, and we did the protocol. For this procedure, we did corticospinal excitability measured with transcranial magnet stimulation, so we stimulated the brain, and we stimulated peripheral nerve. So peripheral nerve at the groin area, we stimulated with electrical stimulation. So if you look at here, there are 2 force transducers which measure force at each leg. We wanted to know how much fatiguing our left leg is going to affect our right leg. And this is the stimulator that we use to stimulate at the level of groin, and transcranial magnet stimulator to measure corticospinal excitability. When I say corticospinal excitability, when we stimulate transcranial magnets, when transcranial magnet stimulate our brain, signals go down and make in our electromyography signal, we are going to see it in the next slide, make a signal called motor evoked potential, MEP. And when we stimulate at the level of peripheral nerve, this peripheral nerve is going to generate another action potential. We call it M wave. So as you can see here, this is one contraction. So contractions are 100% MVC, 100% MVC, 75% MVC, and 50%. And on top of each, we have two stimulations. If I zoom in, you can see that this is MEP and this is Mmax. These are EMG signals, and this is force. So this is force. These two are EMG. So yeah, MEP and Mmax. So I'm not going to go through voluntary activation. If you are interested, I would like to finish my PowerPoints on time. So if you're interested about voluntary activation, I get back to that later. But let me go. The only thing that you need to know, when we stimulate at the level of peripheral nerve, MVC, subjects are pushing as hard as they can, maximum voluntary contraction. When you receive one stimulus, a little force is going to be actually generated on top. It shows that this much, like this much, force deficit comes from your brain. Means your brain couldn't activate all of your motor neurons because electrical stimulation could increase force. Okay, so results. We had 6 sessions. Pre-test. This is MVC force, maximum voluntary force output. These 6 sessions have 6 pre-tests, identical pre-tests. These are different sessions, and the magnitude of pre-test is exactly the same between 6 sessions. So what we are interested to know now is what is the difference between these, two sessions? The only difference is 60 seconds contraction. This is force here. So force didn't change at all when there was a 60 seconds rest. What about if we do a contralateral fatigue? Nope, there is no change. So we killed this leg, practically I should say. This leg force didn't change. Now let's go to this level. We did rest 30 seconds contraction or fatigue 30-second contraction. What is the response? Does this 60 seconds contraction change the force? Nope. And at the last level, here we have only 60 seconds. Here 120 seconds. So back to back, 60 seconds, again 60 seconds. Does it change force? Nope. So what we can say is that force does not change, even though with a very, very demanding task like that. Does our brain work like separate, like islands, like left hemisphere, right hemisphere work totally different without interfering each other? I do not know. So the next thing that we're very interested to, we know that there are 2 contractions here which may change the magnitude of force output at the beginning of these 2 contractions. So 30 seconds contraction, 60 seconds contraction. Here, there is nothing before that. Here, there is a very demanding task before. What's the difference? So we are comparing now the slope. How much is the slope? Reduction from beginning to end of the task. No difference. How about here? 60 seconds contraction. Is there any difference from beginning to the end compared to the resting day? No. There is no difference. This is the first time we are doing this type of demanding, really demanding tasks. I told you, previously everything we did, it was single MVC. But this is not single MVC. This is 60 seconds MVC. But our brain still survives. And the final thing is corticospinal excitability. Okay, how much is the responsiveness of our brain? How much is the excitability inside our brain? Because our brain, what you see as the outcome in our movement is a combination of inhibition and excitation. So this inhibition, like a tug of war between excitation, inhibition. So how much is excitability in our brain? After we tested the identical situation, only the difference 60 seconds contraction, corticospinal excitability increased. It didn't drop. I thought probably it would drop, but no, it increased. But after we had 30 seconds contraction interfering in this protocol, it went back down. But there is no difference between these two. And identically, there is no difference between these two. So the conclusion of my study, the conclusion of what we did, was that brief and sustained contraction, even 5 seconds, 30 seconds, or 60 seconds, doesn't matter. Brain is not going to give up. Fatiguing one side is not going to affect force output in the other side. However, corticospinal excitability increased from one side of the body to the other side. This result, which is increasing corticospinal excitability, actually in another study that I did in 2016, was the same. So after fatigue, corticospinal excitability increased. I think the major reason that corticospinal excitability increases after a fatiguing task is that brain thinks you need to compensate. You are tired, but in order to drop force, I'm going to compensate it. How I compensate? I increase excitability in the brain. And this is a preventive mechanism from further fatigue in our body. So now, the last thing, probably you say, so why it is important? I'm working on MS patients. I know MS patients, they have a lesion in their brain. In one side of their brain, most of them in one side of the brain, they have lesions more than the other side. So we know that when they exercise, the side that has lesion is always the weak point for them. So they're going to give up because of that lesion. I'm thinking the next step that I'm going to do, the next experiment that I'm going to do, is to fatigue or exercise the non-lesion side of their body and see if it's going to improve their performance and it's going to prevent further reduction in their performance and further actually deterioration in their brain. So all of what I said, to me, it's not interesting at all unless you use it in a therapeutic setting, because I really do not care if it affects muscle performance in athletes or not. I don't care. I care how I can use these findings in therapeutic setting. Most probably, it's going to be in MS patients and people with brain stroke. Thank you very much.
Thank you, Jalal. Wonderful presentations. So for the sake of live streaming webinar, you can ask the questions, but Jalal will try to repeat the questions so that everybody on the net can hear it properly. So the floor is open for questions.
John. I always heard that, you know, for rehabilitation and various other types of things, that if you were cast on one limb,
yeah,
that it was a good idea to work out the other limb,
exactly,
because there would be some transference.
Yeah.
Now your work is just with the cortical excitability.
Yeah.
But is there any?
Yeah, it's a very good question. So the question is, if you have a motor deficit in one limb for any reason, probably for an injury, exercising one side is going to improve the other side. Yes, exercising one limb is going to improve strength in the other limb, which is, they call it cross-education, right? But when you're exercising the other limb, you are going to cause fatigue. And how this fatigue is going to affect the other side. So it has two effects: an acute effect, which could be, I showed there was no change, or it could be reduction of force or whatever, but it has a long adaptation as well, which long adaptation could be facilitation of force in the contralateral limb. What you mentioned exactly is called cross-education, and it totally happens. Several studies have shown that exercising one limb can increase 30% strength in the other side of the body. But this is a long-term adaptation. What I do now is short-term adaptation. What happens after one session of fatigue? Yes?
So you looked at cortical excitability with TMS and you used
spinal? Yeah, perfect point. When you stimulate your brain, you are not only stimulating brain, oh, sorry. So yeah, the question is, sorry about that. So the question is, yeah, this is, I think, the question. When you're stimulating the brain, you are not just stimulating the brain. Brain signals are going to go through your spinal cord. How do you want to differentiate between these two? If anything happens, do you think it's because of brain or spinal cord? We don't know. MEP or transcranial magnet stimulation is not going to determine that. Transcranial magnet stimulation is the whole pathway from brain to spinal cord to the muscle. That's why we have another technique. We call it cervicomedullary motor evoked potential, or CMEP, which we stimulate here at the level of caudate medulla. And what our friend says exactly is measuring the excitability of spinal level. So now we have cortical excitability, spinal excitability. We have muscle excitability by peripheral nerve twitch electrical stimulation. When we do mathematical changes or mathematical calculations, you will see which one loses excitability or which one gains excitability. In this study, we didn't do it because we have to stimulate either at the level of medulla or at the level of thoracic, which call it thoracic motor evoked potential. Honestly, it's too painful. I'm pretty sure if we want to do it here, we are not going to get many participants. So next step. But it's a very good point. What you saw is not cortical excitability. It is corticospinal excitability.
So you said you measured the superimposed twitch
Yes.
in the MVCs as well, right?
Yes.
So when you see that increase in excitability, does that mean that people can reduce that superimposed twitch?
Yeah, it's a very good question. The question is, the size of superimposed twitch has any correlation with our brain excitability or muscle excitability? No. So there is no correlation. Your excitability may go up. However, you have drop in your drop in your MVC or increase in size of your superimposed twitch. There is no correlation between your brain excitability and your central motor drive. These are two different things. Central motor drive is how much motor cortical things happen in your brain, or motor cortical excitation happen in your brain and send the signal down and activates your muscle. However, excitability is just the excitability of the nerve cells. These are two different things. Could I answer your question? Yeah? So remember, if your superimposed twitch, which I go back, if you do not mind, here. So if the size of your superimposed twitch, which shows deficit in your voluntary activation, if the size of this is getting bigger and bigger, it shows there is more and more deficit in your brain. Is there any correlation between this deficit and excitability in your corticospinal system? No. There is no correlation. As you saw in our actually data, even though we didn't see, I think it was here. Let me go back. Even though we didn't find any change in force output, corticospinal excitability increased. So the size of our superimposed twitch didn't change. However, corticospinal excitability increased. That's why I say this is a compensatory mechanism. To me, this is the thing that avoids further reduction in your voluntary central drive.
And yeah, the thing that I was thinking is that the reason that the force stays constant is maybe that they could activate more.
Yes, exactly.
Voluntary.
Yeah, that's exactly true. Probably increase in excitability in the brain is going to prevent further reduction or any reduction in your performance. Yeah, I totally agree with you.
That has nothing to do with voluntary activation. So
No. It may prevent, but no. I have measured voluntary activation, didn't show it here. At the same time that, let me show it here. I didn't want to go through this because it's a bit complex. Is this the one?
Before we get complex, can I ask a question just kind of like as a follow-up? Because when you showed that result, you said there is a, initially in your argument, you were arguing that, your brain might get fatigued when you do that.
Yes.
And when I saw your results that the force in the muscle stayed the same, but excitability went up,
Yes.
I interpreted that as, okay, You train the one limb really terribly.
Yes.
Your brain gets fatigued, but at the same time, the excitability goes up.
Yeah.
So your drive from the brain is less, but excitability is up, so the end effect is zero.
Yes, that's true. This is exactly you mentioned, right? Exactly. Yeah, this is totally true.
That's simple.
No, that's, yeah. So even though corticospinal excitability increased, this is voluntary activation. Voluntary activation dropped. But honestly, I didn't put this PowerPoint because now you're going to ask why voluntary activation dropped and forces to stay the same. I don't know. Yes, but
when you have more of an age reflex and excitability goes up, you need less activation to get the same force.
yes,
If you have a system that's more excitable,
Yes.
then you have to drive it less to get the same.
yeah, I understand what you mean exactly now. Yes. So it's a kind of balance between excitability and voluntary central drive.
So you have to show the result, because then what Maurice asked becomes crystal clear.
Yeah. So Dr. Herzog said there is a balance between excitability and your voluntary activation. If your voluntary activation is going to drop, your excitability goes up to eventually compensate and balance out the force output, and probably reverse. Yes, I totally understand and agree with that. Yes.
I'm not sure if that's true. I'm not a
No,
brain person.
I'm not either.
I'm just trying to get a simple.
No, that's totally true. No, it's totally, yeah, it totally makes sense. Yes.
So with the contractions, do you factor that in priming, like the contralateral side? Is that what you're trying to say? And that's why it increases excitability, allows you to decrease voluntary activation, but still at the same force output?
I didn't get your question. Could you please explain a bit more?
So it is that, based on your results, is the actual fatiguing on the contralateral side,
Yes.
left side actually priming for contraction on the right side,
What do you mean priming?
like getting it activated, getting it ready to actually contract on the right side?
This is yeah. So do you mean activating one side of the body is actually increase the brain excitability to, or get ready, get the system amped up to do the task? Is it? It could be. Yeah. So what Graham says, okay, the difference, what is the difference here and here? Here there was 60 seconds rest. Here there is 60 seconds fatiguing contraction. Probably during these 60 seconds rest, it's a very relaxing situation. You're sitting doing nothing. Your system cools down. However, here you are in a fight and flight situation. Is that right? This is what you mean? And this is going to actually prevent your force drop and increase your corticospinal excitability. It could be another interpretation. If you meant this, yes, it could be correct. Because here, after 60 seconds, when we ask our subjects, okay, now we are going to do post-test, they were like, okay, let's do it. But here, they were like, yeah, let's do it. They were like amped up. Probably it's going to affect their corticospinal excitability as well. Yes, it's a good point.
I was wondering, for your follow-up study, how are you going to account for peripheral lesions of the MS patients to see if they...
Yeah. It was a very hypothetical, like it was a big hypothesis that I brought up first. If we want to determine brain lesion specifically, it's not really linked to this presentation, but you can do MRI, and MRI determines how much is the brain lesion and where is it located. And if you do before and after exercise, it needs long-term exercises though. So before and after exercise, if you do MRI, you will see. We have been collaborating with Department of Neuroscience in Foothill Hospital, and they said it's very difficult to convince the hospital facilitators to do MRI. But it's a very good point. If we can do like any kind of task, it doesn't matter, it is bilateral, unilateral, or whatever, and we do before and after, we do MRI before and after the training, and we determine if it's going to actually heal the area, because now there are several evidences that show training is going to actually remyelinate the brain. So if you assume that MS is because of demyelination, exercise can remyelinate. And to be honest with you, this is the only cure, or this is the only intervention that has been found pretty solid now. So if we can do MRI before and after, is this the answer to your question? So peripheral lesions, when you say peripheral, where do you mean? Peripheral, like where?
Like in the arms or in the legs, like nerves?
You mean alpha motor neurons? Yeah. It's not MS. MS is a central nervous system problem. It's in the brain and spinal cord. It's not peripherally. There is nothing happen for MS patients. There is nothing happen in their alpha motor neurons. It's just central nervous system. It's brain and spinal cord. Alpha motor neuron is always intact. Yes. Yes.
How do you define fatigue?
Very good question. How we define fatigue? Like, there are many.
You showed the definition at the beginning.
Yes. Yes. So.
Is that a good definition?
Where is the? If you think, where is that? Fatigue. How I can go up? Oh, here we go. Yeah, yeah. So fatigue is decreasing force and power. However,
based on your results, is that a good definition?
it is the final definition, but I didn't find any fatigue. This definition is good. Reduction in force or power, I didn't find any fatigue. Force didn't drop, so I can say I didn't find any non-local fatigue. Based on this definition.
So the question is it a good definition?
Yeah, I think this is a very good definition, because if you do...
Fatigue the muscles that you didn't find anything.
I fatigued the contralateral limb. I fatigued the ipsilateral limb and force dropped like correctly. So let me show you this slide. This is force, right? I fatigued the limb for 30 seconds and 60 seconds and force dropped. So here force is here when there is rest. This is relative to baseline. There is no drop. 30 seconds fatiguing task, force dropped. 60 seconds fatiguing task, force dropped. But when we exercise the contralateral limb, no, it didn't drop. That's why I say we have to really think about the concept of non-local fatigue. Does it really exist? I don't know. Probably the duration of contraction was not enough. Probably we need to do a way longer contraction to find drop here. But 60 seconds was not enough. Yes, Dr. Edwards.
I just want to get some clarification on the preliminary stuff that you showed. So I think it was your PhD work or postdoctoral work after that. But the stuff that, it was kind of the impetus for this work, where you showed if you do repetitive MDCs,
yes,
you can see a drop in force?
Yeah, it was force.
On the contralateral.
Yes.
So what's the difference between that protocol and then this protocol?
This one?
Yeah, yeah.
This protocol has gaps. This is 5-second contraction, 12 5-seconds contraction. Yeah. So there are 10 seconds gap between each contraction. My protocol was 60 seconds sustained contraction.
So is there some kind of difference between muscle's ability to sustain a contraction versus having repetitive?
Yes, absolutely. There are many central and peripheral changes between these two. It worked for this protocol. It didn't work for my protocol. It shows that probably 60-second contraction is not long enough. That's why I say. So if you calculate this, 12 times 5 seconds, 60? Forget about it. I don't know. So here we have 10 seconds, 5-second contraction, 10-second gap, 5-second contraction, 10 seconds rest. At the end, as you can see from contraction number 8, this is a very good point, but at 60 seconds contraction, it didn't happen. So when we measured the slope, when we measure the slope analysis, so the slope analysis is from beginning to the end. When we measured slope analysis from beginning to the end, there was no difference even after 6. There is like only 2% reduction, but it's not much. It's too non-significant. But why it happens? Very good point. I don't know. I was thinking that this fatigue is going to be exaggerated, means subjects are going to go way lower at the end because this is sustained contraction. There is no gap between contraction. It's a sustained contraction. Level of fatigue at the end of this is going to be way lower than those repeated contractions, but they didn't show anything. There is no difference between these two.
And then you think the level of fatigue for the ipsilateral limb that was actually went through the protocol was similar between the studies?
The difference between these two studies is that this one is leg fatigue arm measurement. I did leg. This is different. So probably the whole contralateral signaling pathway from arm to leg is different from leg to leg. Right? So our legs are big muscles. Arm is a small muscle. From a big to small muscle, or from same muscle groups, there are millions of things that can happen. Yeah, this is a very good point, but I really do not know if the motor pathway or the size of the muscle, is it task specific? Is it muscle size specific? Is it upper lower specific? I don't know.
I never really think about these things, so this is probably an idea question.
No, not at all.
I feel like when we walk around and stuff, we have symmetric movement, right?
Yes.
We do something on the right side and we follow it by something
Exactly.
on the left side.
Yeah.
Symmetric.
Yeah.
Is there anything, any effect on the brain that people know of to deny that symmetry, like that reflection? So if I keep moving my right leg, but I don't
Yes.
satisfy the
You inhibit it.
leg.
You mean you inhibit it, right? So it's a very good question. When we walk, we do not inhibit anything. It just moves. Our central pattern generator moves our legs. We even do not think about it. But here, when subjects were doing 60 seconds contraction in this leg, we consistently ask them to keep these legs silent. So they have to kind of split their thoughts to two parts. At the same time, contract as hard as they can here, and keep these legs silent. This is totally different from our rhythmic movement. It's a very interesting point. What is the effect? I don't know. As far as I know, it needs another study to measure. I didn't have time to measure because we finished this study last week, honestly, and I had to do all this analysis. I have not measured silent period. Silent period shows cortical inhibition. Probably when you are willingly keep this leg at silence, probably inhibition is going to go up, inhibition go down, facilitation goes up, or reverse. Probably something happens like that. But you are totally right. We are willingly inhibit one limb, which is against our nature, right?
I'm thinking also in EEG or fMRI studies.
Yes, exactly. Yeah, the problem with EEG studies is that because when subjects are doing this, I do not have a video to show you. Like they are moving their head, they are moving their body, they are like twisting and turning on chair to do this. EEG is very sensitive to head movement and any kind of movement in your body. So we can do EEG. fMRI is a good point, but we have to make sure that the system that you get into MRI room, there should be no metal. Otherwise, stick to rubbish.
I had actually the same question as Brent. You know, I couldn't reconcile why at the beginning you found an effect and then later on you didn't effect. But if you go back to the results where we found an effect, I guess from the neck to the arm.
To the table that I showed?
No, the result that you just showed, that the one that Brent was asking about. You know, the initial study, there was an effect, exactly.
Yes. There was an effect after a longitudinal contractions.
Yeah. I seem to remember you were arguing that might have to do with, brain fatigue, as you call it, like that.
Yes.
Whatever that means.
Yes.
So my question was then, if you do exactly that experiment, that fatiguing experiment, but you don't do the muscle fatigue with the brain, but you do it, let's say, with nerve stimulation.
Yes.
And so your brain is not involved at all. You just fatigue the muscle like crazy to a similar extent as you do here.
Yes.
Would you then find a different result? Because your relaxed that it all happens?
Yes.
Is it really the brain activation?
Yeah, it's a very interesting. So the question is that now we fatigue the leg with voluntary movements. How about if fatigue the leg with electrical stimulation? So I need to elaborate this concept for you. When we say fatigue, means something happened in your muscle, which the feedback sensory system located in our muscles are going to relay the signal back to our brain. So type 3 and 4, fatigue sensitive feedback system sends signal to our brain and says, hey, be careful, something is happening in your muscle. Is this different? Is this signaling pathway and the reaction of the brain is different between voluntary contraction and just contraction induced by electrical stimulation? It's a very good concept. Probably there could be different pathway. However, remember, voluntary contraction, it is painful, but it's not that noxious. It's not that noxious, but electrical stimulation is noxious. And different pathway of feedback is going to be activated. That one is going to be activated, but pain induced by electrical stimulation. This one is activated by pain induced by accumulation of byproducts like prostaglandins, hydrogen, lactate. Over there, lactate is going to be generated probably, but not that high level because it's not volunteer. And then another question is how many stimuli we have to do to get to this level of fatigue, like drop significant. Is it matched in terms of time with voluntary contraction, or no? You need to contract muscle with voluntary contraction for 60 seconds, but equivalent of it with electrical stimulation is going to be 10 minutes. Yeah, provided that subject can tolerate electrical stimulation, right? A small muscle, yeah. But yeah, exactly. We have done 10 seconds, 7-second tetanus in your lab. It is normal, but it hurts.
It does not hurt.
No.
I have another question.
Yes.
So, did you try to figure out in the contralateral vein whether or not the peripheral properties of the muscle are changed? So, for example, did you do just twitch contraction in the relaxed muscle and look whether or not the contractility of the contralateral muscle before and after the fatigue on the other side was affected?
Yes, that's a totally fair point. Here, this little guy here, at the beginning and end of this contraction, I didn't bring up the results. I didn't have time to analyze it. Sorry about that. But these two little twitches here determine if fatigue in the other leg is going to change the contractile property of the non-fatigue leg. As far as I know, no, it doesn't change. So fatigue in one limb is not going to change the peripheral things in the other leg. Everything happens is central. If anything happens, is central. So these two little guys, we put it here to make sure that we measure contractile property of the...
So those two little guys, show me exactly which ones you compared before and after.
So here, we have one twitch before and one twitch after.
Also the arrow is the twitch there.
Yeah, this is twitch, resting twitch.
And is it a single twitch? Or
This is a single twitch. No, this is a single twitch. Doublet could be a lot better, but it is a single twitch.
Well, if you wanted to look for potentiation,
Yes, exactly.
a single twitch you would see much easier than a doublet or a triplet.
That's exactly true. So Dr. Herzog wanted to know if contraction in one limb is going to change the peripheral, not central, peripheral property of the muscle. As far as I know, it doesn't change it because we kept this leg totally at silence.
I guess that was my question. Do you measure if the leg is actually resting the same with
Yes.
the arm study?
Yeah.
They're totally silent.
Yeah, so
Silent when you
that's
do that.
totally true. When you're doing 60 seconds contraction, it's really difficult to keep the other leg at relaxed position. So we show them the EMG traces to our subject and ask them to look at these EMG traces. Whenever it's gonna go up, keep this at relaxed position. Yes, I think we had a very minimum contraction in the other leg. But I think it was you made a very good point. or it was gram. At the same time, you have to split your thoughts. Inhibit or no, it was it's a very good point. You have to split your thoughts. You have to activate this as hard as you can. At the same time, keep this at relax. I really do not know what neurophysiological measurement can be done to determine its effect. So you are contracting as hard as you can. At the same time, you have to be careful to keep this leg at total silence. It could be a very determining factor.
In the previous study, it showed that fatigue did affect the contralateral limb and the elbow flexion. Did you look at the cortical excitability and the voluntary activation to see what one if those changed compared to what you results?
Yeah, that's true. We didn't do it in that study with Israel. We did it in another study. Corticospinal excitability didn't change. No, yes, we did it with another master students, but it didn't change. I wish I had the PowerPoint to show you, but no, corticospinal excitability, it didn't change. But voluntary force dropped though. Voluntary activation dropped though.
But that could be the explanation then.
Yes.
I mean, when you said I have no idea why this happened, I mean, wouldn't that be?
Yeah, it could be a potential explanation for that. Voluntary dropped, voluntary central motor drive dropped, but corticospinal excitability stays the same. So the balance that you mentioned, Dr. Herzog mentioned, seems to be totally makes sense. Yeah. Yes, in my study, excitability increased. Yes.
So do you think that's a duration thing that you need? So what do you think is causing that excitability?
As far as I know, excitability could be a compensatory mechanism. Why it happens? I think it happens to prevent further reduction or any reduction in performance.
But what causes that excitability?
What causes increasing excitability? So probably.
From your studies, you saw an increased excitability, but from the previous ones, there was no increase.
Yes.
So
Task specificity could be task specificity. Could be the duration of the task, could be the limb that we chose. That one was leg fatigue arm measurement. It's very complex matter. That's why I say I really do not know if we should call it contralateral, even contralateral fatigue. Probably it's contralateral excitation, because it seems when you're fatiguing one leg, other side it causes contralateral excitation, not inhibition. But at the same time, voluntary activation drops. So it's a kind of like difficult situation to determine should we call it fatigue or not.
So you almost like half started to answer this anyway, but I was going to ask whether you know that there's a big difference in the total time of the previous protocol versus yours, because perhaps that would indicate that maybe there's some sort of time-dependent effect where you need to be like your brain gives you sort of a grace period.
Yeah.
Where it says, you know what, now you're clearly not in danger. Now I'm going to start having.
Yeah, exactly. So the question is, should we actually test different protocols with different time durations? Is that right? Yeah, it's a very fair point. Probably if we try another study with instead of 60 seconds, so we tried 60 and 30, didn't work. How about 120 seconds? How about 10 minutes? Probably there is a threshold. Probably there is a threshold that your brain says, okay, from now on, I'm not going to follow you anymore. If you want to go you by your own. I'm not following you. You want to push, but I'm not following you. So yes, probably this is the case. It could be task specific. It could be contraction time specific. There are millions of things that can happen. I think we are at the very beginning of determining contralateral excitation or inhibition mechanism.
So you measure the EMG of the antagonists?
Yes, co-activation for do you mean to? So
because you measure torque.
Yes.
And you could have the same torque but different forces
Yeah.
depending on what the co-activation is.
Yes. So one of the parameters that can affect your performance is that when you are fresh, you are localizing your concentration in the active muscle. When you are tired, due to safety, your brain is going to determine how much more excitation is going to happen in antagonist muscle, which is called reciprocal inhibition or coactivation. So for coactivation, we have measured biceps femoris as well, but I have not analyzed the data yet. Probably after fatigue in one leg, coactivation is going to increase in the other leg. But we need to measure it. I have not calculated the results yet. But yes, after fatigue, in order to increase the stability around the joint, your brain is going to further activate the contralateral limbs, which they call it contralateral activation.
I would have hypothesized the other way around, that you have less force now contralaterally because you are somehow fatigued, and then you don't
co-activate. Yes.
You might actually get the same torque.
Yes.
In actuality, you have less
force. This could be another compensatory mechanism. What Dr. Herzog say, probably at the pre-test you have some co-activation, but at the post-test, because your brain wants to keep the force output, your brain says, okay, I'm going to reduce co-activation to facilitate more power output generates from agonist muscle. Yes, it could be a possible scenario as well.
Any other question for Jalal? If not, let's thank Dr. Jalal again.
Thank you very much. Really appreciate your time.
So please join us back next week at the same time, and we'll have Dr. John Halash sitting here. He will talk about modeling calcium diffusions in three-dimensional sarcomere. And have a good rest of the week, and see you next week.